Hello there, and welcome to the Sleeping Physicist. If you're someone who likes to unwind by thinking about stars, matter, and the quiet structure of reality, you're in exactly the right place. Tonight, we'll let our attention drift gently into real physics and real discoveries. Some of what you'll hear may sound surprising, but all of it is grounded in how the universe actually behaves. And if you enjoy these slow, careful explorations, you're always welcome to like and subscribe. But for now, just get comfortable, let your body rest, let your thoughts loosen a little, and let's begin. What is electricity actually made of according to quantum physics? When you flip a switch and a room fills with light, nothing visible seems to travel from the wall to the bulb. There is no stream you can see, no substance pouring through the wire. Yet something unmistakably real happens. The filament warms, photons scatter into the room, and energy becomes immediately present where it was, not before. This is the everyday face of electricity, familiar enough that we rarely stop to question what is physically taking place. But this simple moment already contains the heart of the mystery, because whatever electricity is, it can move energy without carrying matter across the room. If you were to cut open the wire in the wall, you would not find a glowing fluid or stored brightness waiting to escape. You would find metal atoms arranged in a lattice, quiet and still. And yet, when the circuit is completed, the effect is immediate. This tells us something important right away. Electricity is not something that sits inside wires like water inside a pipe. It is something that happens when conditions are just right. And that distinction between substance and process will quietly guide everything that follows. You might be listening from a bedroom, a couch, or a long night drive, surrounded by devices that depend on this invisible activity. Wherever you are, electricity is already at work nearby, not as a thing you could scoop up, but as an organized behavior unfolding through matter. The moment a circuit closes, charges already present respond together. Nothing new needs to be injected. Nothing needs to rush in from outside. The system simply shifts into motion. This is why the question of what electricity is made of cannot be answered the way we answer questions about wood or air or stone. Electricity does not have pieces in the usual sense. It is not built from blocks. Instead, it emerges from properties that matter already has, responding to forces that extend through space itself. And once that idea settles in, it becomes inevitable that we need to look more closely at what those properties are, and how the smallest charged entities in nature actually behave. If electricity is not a material that flows, then the next place to look is not inside the wire, but inside the idea of charge itself. Careful experiments showed that some objects naturally push or pull on others without touching them. This behavior was called electric charge, and from the very beginning, it behaved less like a substance and more like a tendency, a built-in feature of matter that reveals itself only under the right conditions. Charge is not something an object contains the way a cup contains water. It is closer to a rule the object follows. When two charged objects are near each other, space between them becomes active. Forces appear. Motion begins. Nothing needs to cross the gap for this interaction to occur. The effect is immediate and directional, as if the objects are responding to an invisible landscape already present around them. A useful way to hold this idea is to imagine charge not as paint on the surface of matter, but as a setting that matter comes with, like a note an instrument is tuned to play. The instrument itself does not emit sound until it is struck or bowed, but its structure determines exactly how it will respond. In the same way, charged particles do not carry electricity around as cargo. They simply respond in very specific ways when placed in an electric environment. This shift is subtle but important. Electricity is not made of charge. Charge is what makes electricity possible. Electricity appears when charges are allowed to move, rearrange, or respond collectively. That means the true ingredients of electricity are already present even when nothing seems to be happening. A wire sitting quietly on a table contains just as much charge as a wire carrying current. What changes is not what exists, but how those charges are allowed to behave. Once this is clear, the mystery deepens in a productive way. If charge is a property rather than a substance, then we are forced to ask what kind of thing can possess such a property at all. And that question leads directly to the smallest charge participants in electrical phenomena, entities that do not behave like tiny solid beads, but like something far more spread out and subtle than everyday intuition would suggest. The moment we begin talking about charged particles, one name appears almost immediately: the electron. It is tempting to imagine it as a tiny solid bead sliding through metal, carrying electricity along with it. But quantum physics gently dismantles that picture. An electron is not a miniature object with a clear edge and a precise location. It is a quantum entity, described not by a single position but by a spread of possibilities. Inside a metal wire, electrons do not line up and march forward when a switch is flipped. They already exist everywhere throughout the material, woven into the atomic structure itself. Quantum mechanics tells us that each electron occupies a kind of cloud, a region where it can be found if measured, rather than a point that traces a neat path. These clouds overlap, interact, and arrange themselves according to strict quantum rules. Think of a crowded lake at dawn. The water is calm but not empty. Ripples are possible everywhere at once. When a breeze passes over the surface, no single droplet travels across the lake, yet a wave moves effortlessly from one shore to the other. The electrons in a conductor behave in a similar way. They are present throughout the material, and when an electric influence appears, it reshapes how their collective patterns evolve. This is why electricity does not require electrons to race from the power plant to your home. The electrons near your lamp were already there long before you turned it on. What changes is the way their quantum states adjust in response to an electric influence. They shift slightly, coherently, and together. The motion is subtle, almost unimaginably slow, on the level of individual particles, yet the effect they produce is immediate. Seeing electrons this way dissolves another intuitive misunderstanding. Electricity is not built from electrons as bricks build a wall. Electrons are participants, but the phenomenon itself arises from how their quantum nature allows them to respond as a connected system. And to understand what guides that response, we need to look not just at the particles, but at the invisible structure that tells them how to move, even across empty space. Electrons do not decide how to move on their own. Their behavior is guided by something that exists, even when no particles are traveling anywhere at all. This guiding presence is the electric field. An electric field is not made of matter, and it is not a substance flowing through space. It is a condition of space itself, a structure that tells charged particles how they are allowed to behave at each point around them. When a battery is connected to a wire, what forms first is not a current, but a field. This field spreads through the circuit at nearly the speed of light, reaching every part of the wire almost at once. Only after the field is established do the electrons respond. They do not receive a push from behind. They feel a change in the rules governing their motion, and they adjust accordingly. You can think of the electric field like the slope of a landscape. A marble placed on a flat surface stays where it is. Tilt the surface slightly, and the marble begins to drift, not because something is pushing it from behind, but because the shape of the space beneath it has changed. In the same way, an electric field reshapes the space electrons inhabit. Their motion emerges naturally from that reshaping. This is a profound shift from older mechanical ideas. Electricity is not a chain of collisions or a queue of particles handing energy forward. It is a coordinated response to a field that exists everywhere in the system at once. The field carries the information. The electrons provide the means to respond. Once this is understood, electricity begins to look less like a material flow and more like a conversation between matter and space. The wire supplies charged participants, the electric field supplies direction and structure, and together they produce what we experience as current. To understand what that current truly is, we now need to look carefully at what actually moves and how little motion is required to create such powerful effects. Once the electric field is in place, electrons begin to respond, but not in the way our instincts suggest. They do not surge forward in a rush. They drift, and that drift is astonishingly slow, often measured in millimeters per second. Yet the effect of electricity appears almost instantly. This apparent contradiction dissolves when we recognize that current is not about speed, but about coordination. Electric current is defined as the organized motion of charge. Organized is the important word. In a metal, electrons are already moving constantly due to thermal energy, bouncing and scattering in every direction. That motion is chaotic and averages out to nothing. When an electric field is applied, it does not create motion from nothing. It gently biases motion that already exists, nudging the random dance into a slight preference for one direction over another. An analogy helps here. Imagine a crowded room where everyone is pacing randomly. From above, the crowd goes nowhere. Now, imagine a subtle slope appears beneath the floor, just enough that people begin drifting slightly downhill while still walking randomly. No one moves fast, no one travels far, but a net flow appears. That slow collective bias is what electric current really is. This is why current depends on conditions rather than force. Stronger electric fields do not launch electrons like bullets. They increase the degree of organization, tightening the statistical preference for one direction. More current means not faster electrons racing through the wire, but more charge responding coherently to the same guiding structure. Seen this way, electricity is less like transport and more like alignment. Charges do not need to go anywhere special. They only need to participate together. And once we separate the motion of particles from the movement of energy itself, another quiet surprise emerges, one that explains how electricity can act so quickly, even when its charge carriers barely move at all. At this point, a quiet distinction becomes unavoidable. If electrons drift slowly yet lights turn on instantly, then the movement of energy cannot be the same thing as the movement of particles. In electricity, these two ideas part ways. The electrons respond locally, but the energy moves through the system by a different route altogether. The energy carried by electricity flows primarily through the electric and magnetic fields surrounding the wire, not through the interior of the metal itself. This surprises many people, because the wire feels like the obvious carrier. But experiments and careful measurements show that the energy travels in the space, around the conductor, guided by the fields established by the circuit. The wire's role is to shape and constrain those fields, not to transport energy like a pipeline. A helpful image is to think of a long, flexible belt looped around two wheels. When one wheel turns, the belt moves everywhere at once, even though each point on the belt shifts only slightly. The motion is distributed, coordinated, and immediate. In electricity, the fields act like that belt. They rearrange across the entire circuit nearly instantaneously, carrying energy from source to device without waiting for individual electrons to make the journey. This is why cutting a wire stops power immediately, even though electrons are still present on both sides of the break. The path for the fields has been interrupted. The structure that allowed energy to flow has been altered. Electricity, at its core, depends on continuous field relationships, not on streams of particles crossing long distances. Once this is understood, electricity begins to look less like something made of moving pieces and more like something made of relationships. Charges, fields, and space itself form a system that can store, guide, and release energy. And when we follow that idea deeper, we are naturally led beyond particles altogether, toward a description where fields are no longer secondary, but fundamental. When we follow electricity beyond particles and into fields, we arrive at a deeper layer of physics where even empty space is no longer empty. Quantum physics reveals that electric and magnetic fields are not just mathematical tools. They are real, physical entities, present everywhere, even in regions where no charges are moving at all. In this view, space itself is active. The electromagnetic field exists throughout the universe, capable of carrying energy, momentum, and information. When a circuit is formed, we are not creating something new from nothing. We are shaping a portion of this ever-present field, giving it boundaries, directions, and conditions under which it can transfer energy in an organized way. The quantum vacuum, despite its name, is not a void. It is the lowest energy state of all quantum fields, including the electromagnetic one. Even when nothing appears to be happening, subtle fluctuations persist. Electricity does not emerge from these fluctuations directly, but it depends on the fact that fields are fundamental ingredients of reality, not secondary effects layered on top of particles. An intuitive way to think about this is to imagine space as a vast, calm ocean. Most of the time, the surface looks flat and still, but the ocean is always there, capable of supporting waves the moment wind or boundaries shape it. Electrical systems do something similar. They do not manufacture a field, they organize one. This reframes the original question in a powerful way. Electricity is not made of electrons alone, and it is not made of energy as a substance. It is made of the electromagnetic field responding to charge within matter, structured by materials and guided by boundaries. And once we accept fields as primary, another familiar idea needs careful clarification, because it often gets confused with ordinary electric current, even though it plays a very different role. At this depth, it becomes tempting to say that electricity is made of photons, because photons are the quanta of the electromagnetic field. But this is one of those moments where precision matters. Photons are real, but ordinary electric current is not a stream of photons moving down a wire. Photons appear when electromagnetic fields change in a way that allows energy to detach and travel freely through space. Light is the most familiar example. Radio waves, microwaves, and X-rays are others. In all of these cases, the electromagnetic field has organized itself into a self-sustaining ripple that can move independently, carrying energy away from its source. In a steady electric current, that detachment does not happen. The fields are present and active, but they remain bound to the circuit. Energy flows through the field configuration shaped by the wire and its surroundings, not as individual photons escaping into space. The field is doing work, transferring energy, but it is not breaking into discrete packets that fly off on their own. A helpful way to picture this is to imagine a stretched rope held firmly at both ends. You can transmit energy along the rope by moving one end, and the motion travels through the tension in the rope itself. But unless you snap the rope or shake it violently, no pieces break free. Photons are like those free-traveling waves. Electric current is like the energy moving through a constrained, continuous structure. This distinction matters because it shows that electricity occupies a middle ground between static structure and radiation. It is dynamic, but contained, quantized at a deep level, yet smooth in everyday experience, and it is this balance that allows electrical systems to be both stable and responsive, capable of delivering energy precisely where it is needed. To see how this plays out in real materials, and why some substances conduct electricity easily, while others resist it, we need to look even more closely at the quantum structure of matter itself, where fields and particles meet at the atomic scale. Whether electricity flows easily or struggles depends not on the electricity itself, but on the quantum structure of the material it moves through. Inside a solid, atoms are arranged in repeating patterns, and electrons are not free to occupy just any energy they like. Quantum physics restricts them to specific ranges, creating what are known as allowed and forbidden states. In metals, these allowed states overlap in a way that lets electrons respond collectively to an electric field with relatively little disruption. The field gently reshapes their shared quantum states and current emerges with ease. In other materials, the structure is less forgiving. Electrons encounter gaps where no allowed states exist, and motion becomes difficult or impossible without additional energy. Resistance arises from interaction. As electrons drift under the influence of an electric field, they scatter off vibrating atoms, impurities, and structural irregularities. Each interaction slightly disrupts the organized motion imposed by the field. Energy is not lost, but transformed, often into heat. The warmer a material becomes, the more its atoms vibrate, and the more frequently these disruptions occur. An intuitive way to imagine this is to think of walking through a crowded forest. In an open grove, you can move smoothly with only gentle course corrections. In dense undergrowth, every step requires effort, and forward motion becomes fragmented. The electric field is still present, still guiding direction, but the material determines how cleanly that guidance can be followed. This reveals another quiet truth. Electricity is not a universal substance behaving the same way everywhere. It is an interaction between fields and the quantum architecture of matter. The same electric field can produce vastly different outcomes depending on the microscopic order beneath it. And with that understanding in place, we are finally ready to answer the original question as clearly and carefully as quantum physics allows. At the deepest level quantum physics currently offers, electricity is not made of a substance at all. It is made of a relationship between charged quantum particles, the electromagnetic field, and the structure of space they inhabit. Nothing needs to be poured, injected, or consumed. Electricity appears when these elements align in a very particular way. The charged particles provide the ability to respond. The electromagnetic field provides the rulebook that tells space how that response should unfold. Materials provide boundaries and constraints that shape the field into useful forms. When a circuit closes, these pieces lock together. The field reorganizes. Charges drift in coordinated patterns. Energy flows through space guided by that organization. Electricity exists only while this relationship holds. This means electricity is not stored inside batteries like a hidden fluid. A battery stores energy by maintaining a separation of charge, a tension in the electromagnetic field. When a path is provided, that tension relaxes. The field changes shape. Work is done. Once the separation disappears, the electricity stops, not because something ran out, but because the conditions that allowed the relationship to exist are gone. Seen this way, electricity is closer to a standing pattern than a moving object. It is an active configuration of reality itself, involving matter, fields, and space acting together. Nothing in isolation is electricity, only the interaction is. And quietly, without drama, this brings us to a broader realization. Many things we once thought of as substances turn out to be processes instead. Heat, light, sound, and now electricity reveal themselves not as materials, but as organized behavior emerging from deeper rules. The universe, it seems, prefers relationships over things, patterns over pieces, and gentle coordination over force. Once electricity is understood as a field-based relationship, there is a subtle extension that completes the picture. Electricity does not require charges to move at all times. In certain situations, changing electric fields themselves behave as if a current were present, even when no particles cross the space in between. This insight emerged in the 19th century, when careful reasoning showed that a changing electric field produces a magnetic effect, just as a moving charge does. Between the plates of a capacitor, for example, charges accumulate on opposite sides, but no electrons jump the gap. And yet, the surrounding magnetic field behaves as though a current flows straight through the empty space. What exists there is not motion of matter, but motion of the field itself. A gentle analogy helps here. Imagine stretching a rubber sheet between two supports. You can transmit motion across the sheet by pushing on one side, even if nothing slides across the surface. The tension changes propagate through the material. In electricity, the electromagnetic field plays a similar role. Changes in its shape and intensity move energy forward without requiring particles to make the journey. This idea, often called displacement current, reveals something quietly radical. Electricity is not fundamentally about charges traveling through matter. It is about how electromagnetic fields evolve over time. Charges are one-way fields change. Boundaries are another. Motion of matter is optional. What matters is variation. With this realization, electricity becomes inseparable from magnetism and time itself. Electric and magnetic fields are not separate actors, but two aspects of a single structure that responds dynamically whenever conditions shift. And once time variation enters the story, the distinction between electricity, magnetism, and light begins to soften, opening naturally toward one of the most unifying ideas in all of physics. When electric fields change over time and magnetic fields respond in turn, something remarkable happens. The two begin to sustain each other. A changing electric field creates a magnetic field. A changing magnetic field creates an electric field. And once this mutual exchange takes hold, the pattern no longer needs charges or wires to persist. It can travel freely through space. This traveling self-sustaining pattern is what we call light. This is not a separate phenomenon layered on top of electricity. It is electricity extended. The same electromagnetic field that organizes charges in a wire can, under the right conditions, detach from matter entirely and move outward at a fixed speed through empty space. What changes is not the nature of the field, but the way it is allowed to evolve. You can imagine this like a carefully timed ripple on a calm pond. If the timing is right, each rise of the water reinforces the next, allowing the wave to move smoothly across the surface. In electromagnetic waves, the electric and magnetic components play this reinforcing role for each other, carrying energy without any material support. This unification tells us something profound about what electricity is made of. It is made of the same field that fills the universe with starlight, radio signals, and cosmic background radiation. In a circuit, that field is guided, constrained, and shaped by matter. In light, it is free. But in both cases, the underlying ingredient is the same. Electricity, magnetism, and light are not different substances. They are different expressions of one electromagnetic structure, responding to different boundary conditions. And with that realization, electricity becomes less like a human invention and more like a local way of engaging with one of the fundamental fabrics of the universe itself, quietly present everywhere, waiting only for the right arrangement to reveal its motion. Even though the electromagnetic field is fundamentally quantum in nature, electricity in daily life feels continuous and smooth. There are no visible jumps, no flickers of discreteness, no sense that current arrives in tiny packets. This apparent calmness is not a contradiction. It is a consequence of scale. At the smallest level, electric interactions are quantized. Charge comes in fixed units. Energy exchanges occur in discrete amounts. Fields themselves can be described in terms of quantum excitations. But in a typical electrical system, the number of participating charges is enormous. Trillions upon trillions of electrons respond together. Their individual quantum steps overlap so densely that the result appears seamless. A useful image here is rainfall. A single raindrop is discrete and countable, but in a heavy rain, the drops arrive so continuously that the air seems filled with water. You do not experience drops, you experience rain. Electricity works the same way. Quantum events are happening constantly, but their collective behavior forms a smooth, predictable flow. This is why classical electrical laws work so well. They are not wrong, they are average descriptions of vast quantum activity. Voltage, current, and resistance emerge as stable patterns because the underlying quantum fluctuations cancel out statistically, leaving behind a calm, reliable structure. Understanding this resolves a lingering tension. Electricity is not secretly classical beneath the surface, nor is it visibly quantum in everyday use. It is quantum behaving collectively, where the rules of probability give rise to order, and that quiet emergence of smoothness from discreteness hints at something broader about the universe, where continuity is often not fundamental but earned through scale and cooperation. One more layer quietly completes the picture. Electricity is not only about what exists in space, but about how patterns persist through time. A steady current is not a frozen arrangement, it is a continuously renewed order, maintained moment by moment as fields and charges respond to each other without interruption. At every instant, electrons scatter, fields adjust, energy redistributes, and yet the overall pattern remains stable. This stability is not imposed from outside. It emerges because the electromagnetic field and the material respond faster than disturbances can disrupt them. The system constantly repairs itself, smoothing out microscopic chaos into macroscopic calm. You can imagine this like a murmuration of birds at dusk. Each bird moves independently, responding only to nearby neighbors, yet the flock holds a coherent shape that flows smoothly across the sky. The shape is real, but it is not stored anywhere. It exists only because the underlying responses continue without pause. Electricity behaves in the same way. Its order lives in time, not in objects. This reveals why electricity stops the instant a circuit breaks. Nothing needs to drain away. The organized response simply can no longer be sustained. The field loses its boundary conditions. The coordination dissolves. What remains are the same particles and the same space, but without the pattern that made electricity present. Seen this way, electricity is not something the universe contains. It is something the universe can do. It is a temporary alignment of fundamental ingredients, held together by cause and effect unfolding across time. And in that sense, electricity becomes an example of a broader theme woven throughout physics, where reality reveals itself less as a collection of things and more as a choreography of relationships that exist only while they are continuously maintained. Electricity feels familiar because it is measurable. We place probes on wires, read numbers on displays, and speak confidently about volts and amps as though we were directly touching the phenomenon itself. Yet in quantum physics, measurement is never a passive act. To measure electricity is not simply to observe what is already there, but to interact with a system in a way that inevitably changes it, even if only slightly. When we measure an electric current, we are not detecting electrons one by one. We are registering the macroscopic consequences of countless quantum interactions averaged together. The measuring device couples to the electromagnetic field, draws a small amount of energy, and responds according to its own physical design. What we read is not electricity in isolation, but electricity as it appears through a particular kind of interaction. At the quantum level, this distinction matters. An individual electron in a conductor does not have a sharply defined trajectory that could be traced without disturbance. Its behavior is described by probabilities, not paths. Any attempt to localize it precisely requires an interaction that alters its state. This is not a technological limitation, it is a structural feature of how quantum reality works. A useful way to hold this idea is to imagine trying to map the exact pattern of ripples on a still pond by touching the surface with your finger. The moment you make contact, the pattern changes. You can learn something real about the water, but never without becoming part of the system you are probing. Measuring electricity works the same way. The act of measurement participates in the field configuration it reveals. This is why electricity resists being reduced to a list of microscopic ingredients. At no point can we freeze the phenomenon and point to a piece of it without altering the conditions that made it exist. We can measure voltage between 2 points, but that measurement depends on the reference points we choose. We can measure current through a wire, but only by allowing some interaction to occur. Electricity is always contextual, always relational. Quantum physics sharpens this insight further by showing that even the electromagnetic field itself cannot be fully specified everywhere at once. Field values fluctuate. Energy densities have limits imposed by uncertainty. The more precisely we define the electric field in one region, the less precisely we can define its behavior over time. This does not make electricity vague or unreliable. It makes it deeply structured by the logic of measurement. In everyday engineering, these subtleties fade into the background. The collective behavior is stable enough that electricity behaves predictably. Circuits can be designed, power grids can be synchronized, devices can be trusted. But beneath that reliability lies a restless quantum foundation that never quite settles into a fixed picture. This has an important implication for the original question. If electricity is not a substance and not a collection of particles and not even a static field configuration, then asking what it is made of begins to resemble asking what a wave is made of as it passes across water. The wave is real, its effects are measurable, but it is not built from a separate material beyond the medium and the rules governing motion. Electricity is made of the electromagnetic field behaving in time, constrained by matter, revealed through measurement. What we know of it is inseparable from how we interact with it, and far from being a weakness, this is what allows electricity to be so versatile. Because it is not a thing, it can take on many forms. Because it is relational, it can be shaped to our purposes. Because it is field-based, it can act across space with astonishing coordination. As we continue deeper, this perspective opens naturally toward questions not just about energy and matter, but about information itself. Because whenever electricity changes, whenever fields reorganize and charges respond, something else changes as well. The state of the system encodes information, and in modern physics, electricity has become one of the most precise ways we have of storing, transmitting, and transforming that information, linking the quiet flow in a wire to the deepest questions about what can be known, recorded, and preserved in a quantum universe. When electricity flows, something more than energy moves through a system. There is also information. Not information in the abstract sense of meaning or message, but physical information. the precise state of a system that distinguishes one configuration from another. In quantum physics, this distinction matters because information is not just descriptive, it is something that must be physically embodied. Every electrical state corresponds to a particular arrangement of charges and fields. A wire carrying current is physically different from the same wire at rest, even if the difference is subtle. Voltages encode differences in an electric potential. Currents encode coordinated motion. Switches, gates, and circuits exist to control these configurations, to select which states are allowed and which are not. Electricity becomes a language written in the grammar of fields. This is easiest to notice in digital electronics, where electrical states are deliberately limited to a small set of possibilities. A high voltage here, a low voltage there. On and off, 1 and 0. But beneath that simplicity lies continuous physics. The field does not know it is carrying a bit. It only responds to boundary conditions. Yet the stability of those conditions allows information to persist reliably through time. From a quantum perspective, this persistence is remarkable. The electromagnetic field is dynamic and responsive, yet it can be shaped into patterns that resist noise, decay, and uncertainty long enough to perform meaningful work. This is possible because information in physics is always protected by structure. Energy, barriers, field configurations, and material properties work together to stabilize certain states against random disturbance. A helpful way to picture this is to imagine grooves carved into a landscape. A marble placed near a groove may roll around unpredictably, but once it settles into the groove, its motion becomes constrained. The groove does not stop motion, but it channels it. Electrical systems create grooves in the space of possible field configurations. Information is the choice of which groove the system occupies. At the deepest level, this is still electricity behaving as a field. No new ingredient has been added. But the emphasis shifts. Electricity is no longer just something that delivers energy to a motor or a bulb. It becomes a way of holding distinctions in place, of maintaining differences that would otherwise blur. Voltage differences store information. Current changes propagate information. Circuits exist to shape how that information flows. Quantum physics adds another layer of subtlety. Because fields fluctuate and particles behave probabilistically, information cannot be copied arbitrarily without cost. There are limits to how precisely an electrical state can be known, how quickly it can be changed, and how perfectly it can be preserved. These limits are not engineering failures. They arise from the same quantum structure that gives electricity its power. This is why heat generation is unavoidable in ordinary electrical systems. Every time information is erased or reset, every time a system is forced into a particular state, regardless of its previous configuration, energy is dissipated. The electromagnetic field rearranges itself, and that rearrangement leaves traces in the surrounding environment. Electricity is not just a carrier of information, it is part of the bookkeeping that keeps track of what the universe has forgotten. Seen this way, electricity becomes entangled with time itself. Information distinguishes past from future. A stable electrical state records something about what has happened. A change in current marks an event. The flow of electricity through a circuit is a physical history unfolding, each configuration giving way to the next, according to deterministic rules shaped by quantum uncertainty. This perspective also reveals why electricity is so deeply woven into modern physics. From particle accelerators to quantum computers, from detectors measuring cosmic radiation to instruments probing the structure of atoms, electricity is the medium through which information about the universe is gathered and processed. Fields respond, charges move, signals form, knowledge emerges. And yet, despite this central role, electricity itself remains humble. It does not demand interpretation. It does not carry meaning on its own. It simply obeys the rules of the electromagnetic field, responding faithfully to conditions imposed by matter and geometry. Meaning arises only when systems are arranged to use those responses in particular ways. As the picture deepens, electricity appears less like a commodity and more like a capacity of the universe to support stable, controllable patterns of field behavior that can move energy, encode information, and persist through time. And once electricity is seen as a physical expression of information flow, the boundary between physics and computation begins to soften, inviting a final, deeper question about whether the patterns carried by electricity are merely tools we use, or whether they reflect something fundamental about how reality itself processes change. Once electricity is understood as structured field behavior, carrying information through time, a deeper idea comes quietly into view. Electricity does not merely respond to the universe, it participates in how the universe processes change. Every electrical interaction is a physical transformation governed by rules, constraints, and allowed transitions. In that sense, electricity behaves like a kind of computation, not symbolic or abstract, but embodied directly in matter and fields. At its core, computation is the transformation of one physical state into another, according to consistent rules. In a circuit, this is exactly what happens. An input voltage leads to a rearrangement of fields. Charges respond. A new configuration emerges. Nothing symbolic is required. The physics itself performs the transformation. Electricity does not represent the computation. It is the computation. This idea becomes clearer when we look at logic gates, the basic elements of digital devices. A gate does not know it is performing logic. It simply has a physical structure that allows some electrical configurations to persist and others to collapse. The laws of electromagnetism and the quantum structure of materials ensure that certain inputs reliably produce certain outputs. What we call logic is a human interpretation layered on top of a physical process that would occur whether or not we named it. A helpful analogy is a river encountering a fork in the terrain. Water follows the channels available to it. Rocks and slopes determine which paths are accessible. Over time, stable patterns of flow emerge. The river is not choosing, it is obeying physics. Electricity behaves in the same way. Circuits carve channels in the space of possible field configurations, and electrical states flow along those channels. Quantum physics adds an important refinement. At very small scales, electrical states are not infinitely divisible. There are limits to how finely information can be encoded and how quickly it can be transformed. Quantum uncertainty places bounds on precision. Energy-time relationships limit speed. Noise and fluctuation are unavoidable. Computation, like electricity, is constrained not by imagination but by physical law. This leads to a striking realization. The limits of computation are not imposed by technology. They are imposed by the electromagnetic field itself and its quantum nature. Every electrical operation, no matter how abstract it seems at the software level, ultimately reduces to charges responding to fields under these constraints. The universe does not allow arbitrary transformations. It allows only those consistent with its fundamental structure. From this perspective, electricity becomes a bridge between abstract rules and physical reality. It is how logical distinctions are enforced by nature. A bit is not just a concept, it is a difference in field configuration. An operation is not just a step in an algorithm, it is a rearrangement of energy in space and time. This view also reframes the relationship between electricity and time. Electrical processes unfold irreversibly in ordinary conditions. Heat is generated, energy spreads. Information about precise microscopic states is lost to the environment. This irreversibility gives electrical computation a direction. Causes precede effects. Inputs lead to outputs. The arrow of time is written into the physics of electricity itself. Yet at the deepest level, the underlying laws remain reversible. The electromagnetic field equations do not distinguish past from future. It is the collective behavior, the interaction with vast numbers of degrees of freedom, that gives electrical processes their forward march. Electricity, like time, emerges from coordination and scale. This brings us to a subtle but powerful thought. If electricity is a way the universe processes change locally, then every electrical system is a small region where the universe's rules are being actively enacted. Circuits are not separate from nature. They are nature arranging itself into predictable patterns. The same field that carries signals through a computer chip also carries light across interstellar space. The same charge that drifts in a wire shapes the structure of atoms. In this light, Electricity loses any sense of artificiality. It is not a human-made force harnessed from outside nature. It is a mode of behavior that has always existed, waiting only for the right configurations to make it visible. Humans did not invent electricity. We learned how to participate in it, and once electricity is seen as a physical expression of how the universe transforms states, a final quiet insight begins to form. The difference between matter at rest and matter, alive with electrical activity, is not the presence of a new ingredient, but the presence of sustained organization. Electricity marks regions where the universe is doing something structured, rather than settling into equilibrium. That structure can power a lamp, encode a thought, transmit a signal, or measure a distant star. But beneath all of these uses lies the same fundamental truth. Electricity is the electromagnetic field in action, shaped by matter, unfolding through time, carrying energy and information according to rules written into the fabric of reality itself. Electricity only appears when balance is disturbed. This may sound simple, but it reaches deep into the physics of how systems behave. In perfect equilibrium, nothing flows. Charges distribute themselves evenly. Fields settle into their lowest energy configuration. No current exists, not because anything is missing, but because nothing has a reason to change. A voltage is not a thing added to a system. It is an imbalance maintained against this natural tendency toward uniformity. When one region has higher electric potential than another, the electromagnetic field stores energy in that difference. Electricity happens when the system is allowed to relax, when the field reorganizes itself toward equilibrium and, in doing so, performs work. This is why batteries matter. A battery does not create electricity directly. It does chemical work to separate charge, pushing the system away from equilibrium and holding it there. That separation stores energy in the electromagnetic field. When a circuit is completed, the field responds by driving charges in a coordinated way, reducing the imbalance while transferring energy elsewhere. You can think of this like water held behind a dam. The water is not flowing while the barrier stands, yet energy is present in the height difference. When a channel opens, flow appears, not because water has been created, but because an imbalance is allowed to resolve. Electricity follows the same logic, except the height difference exists in electric potential rather than physical elevation. This framing clarifies why electricity is inherently directional in practical systems. Current flows from regions of higher potential toward lower potential, not because electrons prefer one direction, but because the field is relaxing. The direction is set by the gradient in potential, the shape of the stored energy landscape. Quantum physics does not change this picture, it refines it. The separation of charge, the maintenance of potential, and the relaxation toward equilibrium all occur through quantum interactions. Chemical bonds break and form. Electrons rearrange their allowed states. Fields shift accordingly. The drive toward equilibrium remains, but the mechanisms become more precise. This also explains why perpetual electrical motion is impossible without continuous input. Left alone, all electrical systems decay toward equilibrium. Currents stop, voltages vanish, energy spreads into less useful forms. Electricity exists only while imbalance is sustained, either by external work or by slow processes that have not yet completed. Seen this way, electricity is not a natural resting state of matter. It is a transient condition, a moment when the universe is still in the process of evening things out. What makes electricity powerful is not that it defies equilibrium, but that it allows us to guide how equilibrium is approached, shaping the path energy takes as balance is restored. And so, as everything begins to settle, electricity reveals itself not as a hidden substance waiting inside wires, but as a quiet, ongoing act of balance and release. It is the universe responding to difference, a field adjusting, charges easing their way through space and matter, as equilibrium patiently reasserts itself. Nothing about electricity needs urgency. Even when it powers something fast or bright, its foundations are calm. Fields change smoothly. Particles respond statistically. energy follows gradients that were set long before any switch was flipped. What feels instantaneous to us is simply the coordinated response of space itself, unfolding according to rules that have always been there. Seen this way, electricity is not separate from the rest of physics. It is a familiar doorway into how the universe behaves everywhere. The same electromagnetic field that drifts energy through a wire also binds atoms together, carries sunlight across millions of kilometers, and hums quietly in the background of empty space. Nothing new is added when electricity appears. Something already present is simply allowed to move. This is why the question of what electricity is made of slowly transforms as we follow it. At first, it sounds like a question about ingredients, but in the end, it becomes a question about relationships, between charge and field, between imbalance and flow, between structure and change. Electricity exists not as a thing, but as a moment when those relationships line up just right. When the alignment fades, electricity fades with it. The particles remain, the field remains, space remains. Only the organized motion disappears. And that disappearance is not a failure. It is the universe completing what it set out to do, smoothing differences, spreading energy, resting once more. Perhaps that is why electricity feels so intuitive once we stop forcing it into the shape of a substance. It behaves the way many things in nature behave. Rivers flow downhill. Heat moves from warm to cool. Electricity follows gradients written into fields. None of these are objects. All of them are processes. So when you notice electricity again, in a quiet room lit by a single lamp, or in the gentle warmth of a device resting nearby, it can be seen not as something rushing or burning, but as something settling, a subtle reorganization of the electromagnetic field, a calm negotiation between matter and space, a reminder that much of the universe's activity is not loud or dramatic, but patient, orderly, and quietly precise. And with that understanding in place, there is nothing more that needs to happen. The question has done its work. The picture is complete enough to rest with. The field, as always, continues on its own.